Welcome to video 5 looking at FlexRay. Now FlexRay has a maximum speed of 10 megabit per second, so now we're moving up a gear. What is FlexRay? It's a twin wire differential bus, so identical to CAN in terms of the construction, driven to 3.5 and 1.5 simultaneously, so we have a plus 2 volt differential, and 1.5 and 3.5. So we have a minus 2 volt differential from a recessive voltage of 2.5. And again, this is all doing this for binary signaling and hence communication. So you'll see there in the bottom diagram that we have plus 2 volts, minus 2 volts. Completely different in terms of what we've seen with other differential networks, namely CAN. Termination, of course, because it's twisted pair, slightly different to CAN, but 100 ohms, 100 ohm resistance at each end of the bus. Communication is bidirectional and deterministic, whilst accommodating event-triggered messages. So what do we mean by that? Remember, with CAN, you have to win arbitration. So the computer with the highest priority is the one that gains access to the bus. But with deterministic, everybody has a slot allocated to them for them to speak. It's called a transmit opportunity. So yeah, deterministic, but it can also accommodate event driven, because we can't predict what event maybe need to be transmitted on the bus. So bear that in mind, deterministic. Baud rate, well, again, 10 megabit per second, and you would calculate that by measuring the smallest bit.
And it's that speed that allows the deterministic protocol.
Yeah.
No one's going to have to wait long to speak.
No. That's a good point, actually, because you think, well, okay, what if I've got something important to say, but it's not my turn to say it? Well, there is plenty of bandwidth here for all eventualities. So why do we have FlexRay? Modern vehicle design, again, isn't it? It's forcing us to go this way. We need faster networks. Drive-by-wire systems demand a deterministic, fault-tolerant, high-speed network to ensure seamless and uninterrupted communication. FlexRay provides all the above requirements at 10 megabit per second. So we think we've got it accommodated, and I think we have, but we'll see as we move on through this series of videos. FlexRay was developed by a consortium of vehicle manufacturers to ensure all the requirements above were satisfied, whilst providing the flexibility to customize the data exchange. So again, I've said it before in previous videos, it would be great if everyone spoke the same language and we could read the data, but not so. We're going to have to dig into the encoding and attempt to decode. Now, we can decode with Pico, but when I say decode, I'm almost thinking of converting what we've captured into human readable. Again, it's fault tolerant in harsh environments. The twisted pair is chosen for that reason. It has ISO approval documentation under 17458. So you mentioned earlier.
Yeah. Once again, this is just an overview. It'll get you going. If you want to go see some more information, there'll be some in the supporting material. But if you want to do your own research, that's the standard.
Yes.
And it's not necessary to understand it all, but there are, once again, some diagnostic gold once you dive in that little bit deeper.
Thank you, Annie. You're absolutely right. I don't think you could understand it all because you would go mad.
Yeah, I think so.
I thought Linbus would be quite quick and slick, but just diving into Linbus, so yeah, you can't know it all. But there is information out there. Just-in-time learning is something you mentioned. FlexRay can be used in both star and bus topologies and a combination of both. So manufacturers have flexibility to use FlexRay in different topologies, as we mentioned in video 1. So where do we find FlexRay? I'm going to say prestige vehicles, but we see it now on pretty much most vehicles, certainly of a certain brand. Various brands have adopted this. So maybe not so much prestige vehicles, but where we have demanding onboard systems such as brake and steer by wire and advanced safety pre-crash systems such as ADAS. So really everything.
Yeah. Now, I think it was introduced on the BMW X5, was it?
I don't know.
I believe so. Yeah.
I should have done my research there.
So yeah, so it goes back quite a while, but yeah, nowadays with the determination of sort of the proliferation. Well, let me say that again. Mm-hmm. Nowadays with things like ADAS becoming far more sort of standard. A faster network was required, and that's where we start to see the proliferation of FlexRay.
And that's where FlexRay is chosen for that reason. Yeah. Whilst the consortium of vehicle manufacturers responsible for the development of FlexRay included BMW, Daimler, Chrysler, GM, FlexRay, there's also Bosch in there as well. Yep. They're all part of that, and there's others. It's now incorporated into many other prestige brands, so it's not solely for these vehicle manufacturers. Don't think that because you've got another brand, it's not likely to have FlexRay. The opposite is probably true. FlexRay can be found in vehicles from 2006 onwards and remains in current use today. And yeah, I've put this in. FlexRay should be considered a complement to CAN and not a replacement for.
Yeah, because not everything needs this speed, therefore this cost.
Yeah.
And therefore that's why, you know, in the previous CAN video I said I still see CAN continuing for many years, and that's the reason. It's going to come down to cost. The faster the network, the more it costs.
Yeah. It's something you mentioned there, that not everything needs a fast network. There was a little piece from the team at Intrepid who mentioned that 80% of network traffic requires a bandwidth of less than 10 meg.
Yeah.
Yeah, so here we are talking about getting faster and faster and faster, when the reality is the majority of traffic doesn't need to be anywhere near that speed. So how does FlexRay communicate? The FlexRay bus is held in the recessive state, 2.5 volts, via the FlexRay transceivers inside each ECU. That's the bus idle state. Again, this will sound very familiar. Transceivers drive the bus voltages on the twisted pair of wires to differing levels. You'll see something here, a terminology called BP and BM. They are bus plus and bus minus. So bus plus is FlexRay high, shall we say, at 3.5 volts, and bus minus at plus 1.5 volts. And then they're reversed, which gives us this minus value, again, during signalling where communication is taking place. Subtracting BP from BM, bus plus, from bus minus, returns that differential voltage of plus 2, minus 2, which generates the logic 1 or 0. FlexRay utilises 4 bus states, which we've got listed here. We've got recessive, which is where the, we call it recessive state idle and low power mode. This is where the bus plus and the bus minus are at 0 volts. So 0 minus 0 gives us 0. Then there is the idle state. This is not low power mode, so we almost like standby, where bus plus and bus minus is at 2.5 volts, which gives us a differential of 0 volts. So you would ask yourself, well, how can it determine which of those modes it's in? Well, it actually looks at the voltage range, because 0 minus 0 means you are at 0 volts at 0 range. 2.5 minus 2.5 is 0 volts, but you're at the 2.5 volt range when you start, so that's how it determines which is which. Now this takes a little bit of getting your head around, because I struggled with this. Dominance 0 and 1 are the same. Let me explain that. When bus plus is at 3.5 volts and bus minus is at 1.5 volts, we have a differential of plus 2 volts. When we have data 0, logic 0, bus plus is at plus 1.5, bus minus is at 3.5. So we take away a higher value from a low value, you get a minus value. But in both states, they are considered dominant. The only time the bus is recessive is when the differential voltage is at 0 volts. And we see that here in the diagram on the right hand side, where we have the logic states 1 and 0. the differential in the middle, the recessive value of 0 volts, and how we achieve those states, 0, logic 1, using the differential. So what are the characteristic features of FlexRay? A FlexRay network can accommodate 22 ECUs, nodes, on a bus length of 24 meters. So there seems to be a compromise there, that we've gone up in speed, but we've come down in bus length and the amount of nodes that we can get on the bus. FlexRay transmits according to a predefined time schedule, i.e. every node has its turn. With that said, FlexRay can accommodate event-triggered messages. We call that dynamic data. So anything that's predefined and scheduled is considered static. We know that we're going to update the temperature every so many seconds, whatever it may be. We schedule that and we let that get onto the bus when required. However, when there is a pre-crash condition, that's an event-triggered message, there's room for that message as well. That's considered dynamic, alongside scheduled. Plenty of room on the FlexRay bus. FlexRay ECUs keep their internal clocks precisely synchronized to ensure the messages remain on schedule. We have got to have tight synchronization here when we have an event-triggered event. Everything has got to be perfectly aligned. So there are sections within a packet that ensure this timing is absolutely rock solid. Now, whilst FlexRay delivers many benefits to vehicle manufacturers, it comes at that route, the higher costs and complexity as well. So it's all well and good having these super speed networks, but there is a trade-off.
As always. As
always, yeah. FlexRay can share data with other networks, of course. So if we wanted to get something from FlexRay over to CAN, we pass it through the gateway module, the translator, and it shares that information accordingly. And there we have a complete FlexRay packet to a CAN packet. Chose CAN. Classic CAN, remember, 8 bytes maximum in the payload, whereas with FlexRay, 254 bytes of data in one packet. I mean, that's enough data to be going on with, I would have thought, but there are systems out there that require this level of bandwidth, of this level of data. Okay. So what does a FlexRay look like? What does a packet look like? Here we have the complete packet, and we've split this up so we can actually drill down a little bit more. As Andy mentioned earlier, if you want to go deeper with this, you can do, but we'll give you the fundamentals with this overview of FlexRay. A FlexRay packet consists of 3 major segments. So we have the header, which is further divided into the following sections. So number 1, you'll see it there on the right hand side. It's got quite a few segments all contained in what we class as the header. So we've got reserved and indicator bits. That's about describing the packet content, what's about to come. The frame ID defines the position or message priority. Now that's what we're interested in, as we are interested with CAN and with LIN.
Absolutely, yeah.
The frame ID, there's our little bit of gold to look for. The payload length, the number of bytes in the payload. Now there is also error checking of the header. So this is how tightly things are controlled, whereas before we've waited for the entire message to come through before we've placed that error check code on the end of the message. FlexRay is checking the header first for errors and then proceeding with the rest of the message. We have something called the cycle count. So we talked about deterministic. Everything comes round on a cycle, and you'll see these cycle counts being incremented in the Pico decoder table, so we'll know what cycle we're on. There's the payload next, with 0 to 254 bytes in a single FlexRay packet. And then the trailer, this is section 3. The trailer includes the error check code, another check code, so a double check, but this time of the header and the payload. So double checking everything is good from transmission to receiver. And once again, This time we're measuring the smallest bit to find the baud rate. The smallest bit, 100 nanoseconds. We're drilling right down now.
Oh, yeah.
With excellent resolution. Use the zoom feature, measure the smallest bit, gives you 10 kilohertz, 10 megabit per second.
So just a quick summary on this, because it can get a little bit
heavy.
Yeah, a little bit confusing. Where's the diagnostic goal? Why would we measure it? So it's not just this to see the integrity of the signal. We also can find some stuff out, especially when we start to use the decoder. And there are obviously error messages that we can use, but once again, as you identified when you spoke about it, the frame ID is important, because we can start to identify what is or isn't on a network.
Yeah.
Or by, as you said before, we can remove something from the network and see which ID disappears, and then we can start diagnostically to see what's going on by taking a measurement and using the decoder.
That's something you mentioned earlier, was finding out who's on the network, and that was you would take a capture of data. If you'd got a known good example, so you've got a vehicle, you've got a FlexRay capture, and then all of a sudden you've got a vehicle where an ECU or a node is offline. Take that capture, compare it with known good, look for the missing link, look for the missing one out. There'll be maybe an ID that is present on the good capture that's not there on your capture. Or ultimately use the export feature, which we'll come to. So FlexRay tips. FlexRay ECUs will interpret a differential voltage from minus 0.2 to plus 0.2 as recessive. So we talked there about where you'd got to be for recessive voltage. There is flexibility on that. You can go either side of that 0 volt. We said that it's got to be plus 2 or minus 2. Well, the reality is it will see anything at plus 6 and above as dominant as logic 1. And anything as minus 6 as dominant again, but logic 0. The time span of a smallest bit reveals the baud rate. So am I measuring the right network? If you've got the smallest bit that's 100 nanoseconds, that's not likely to be CAN. So that is FlexRay territory. The frame ID will be or can be linked to an ECU, whilst also indicating priority. The lower the frame ID, as we can, the higher the message priority. All ECUs receive transmitted data on the FlexRay bus. Whether it's relevant to them or not, they will receive the message. Voltage deviations in a FlexRay packet may provide a means to identify ECUs. You might, again, if you're watching the series of videos, that seems to ring true with everything that we work on. They all have these signatures, you call
electronic signatures.
Electronic signatures that reveal within those packets that it could be from this particular ECU, because they all have the same level. Total network impedance, well, 2 100 ohm resistors in parallel equates to half of that value, 50 ohms. Now, current flow in a FlexRay bus branch, remember it has to be a branch, not the spine, flows from an ECU on B plus and to an ECU on bus minus. Trying to use a current clamp on FlexRay, it's possible, but it has a few issues that we'll demonstrate, simply because the bandwidth of the current clamp is 20 kilohertz and above in some instances, where FlexRay we're up at 10 megabits per second, we're at 10 meg. So in which case we want to be, well, we're outside the range of the current clamp. That's not to say we can't use it. Let's try it, let's see what we can find. And discrepancies in signal voltages are typical characteristics of the network and attributed to component inductance and capacitance, as we mentioned before. FlexRay will tolerate overshoot and ringing. There does come a point where if that gets excessive, it will start throwing errors. Interestingly enough, we will demonstrate this, your measurement can intrude such that you can affect the network by measuring, by intruding, a level of intrudence. So on that note then, we'll go into the workshop and we'll carry out some FlexRay diagnosis and examine some FlexRay techniques with PicoScope. Welcome to this video now looking at FlexRay, so high-speed networks. This is 10 megabit per second. We don't have a fault on this car. We're going to discuss really measurement techniques, but where we are with this, Andy, would be our messages being sent.
Yeah, so of the CAN network process, we're going to skip straight to our messages being sent, and we're going to focus on high-speed measuring techniques.
Yeah. So just to play devil's advocate, really, let's start by measuring with a ×1 test lead on a high-speed network. So we're not going to use any guided tests. If you were using the guided test, it would ask you to use ×10. I want to show you what happens on FlexRay when you use a ×1 test lead. So this is reference to ground. We'll choose FlexRay high, or BP as it's called, B+, and we're going to be on, let's try 5 volts. And I'm just going to turn the ignition on, or at least, actually with this vehicle, all we have to do is operate the remote, and we see there that we've got FlexRay activity. And let's just go back through the buffer, and we'll zoom in on a packet. And I think, what's your first impression, Andy, of that?
Yeah, it's not the best, Steve.
No. Let's first of all, let's change sample rate.
Yeah, so if you didn't know any better, you would think, oh, hang on, this is a fast, high-speed network. Do I need a different sample rate? I suppose, what's a good rule for sampling, Steve?
Sample rate is 5 times the frequency. So this is 10 meg, so 5 times that, 50.
50 million?
Yeah, 50 million samples per second. So we'll go into sampling. And once again, you wouldn't have to worry about this if you're using the guided test. That it's all there in terms of configuration of the scope and the correct probe. But
I think it's valuable to show people what would happen if you just approach FlexRay like you would a canvas fault. And it's probably worth noting that using this measurement technique is good for speeds up to. Using the normal ×1 lead is good for?
That's a great question. So for CAN, you're fine there. 1 meg CAN, I think really, for me personally, I get anything above 500 kilobit per second. So for your classic CAN, fine. When you get to CAN FD, which is up to 8 meg, then go for a ×10 probe. Thanks for that. We'll take a reference of what we've done first of all. So this was ×1 on a low sample rate. And let's just drag this down here, and now we've changed the sample rate to 50 million. The vehicle has gone to sleep, so let's just operate the remote, wake the network back up. It looks better already. Sorry, let me move those out the way. And we'll zoom in. So it's now looking much sharper in terms of edges, almost like, it's starting to form a packet, I would say.
You can almost see what's going on there, but there's an incredible amount of ringing noise.
Overshoot. And we discussed this before. It's quite common. The system can tolerate that, but is that now the system, or is it our probe? Are we influencing the signal? We'll take another reference waveform, and we'll keep that one on, because we know that that one is 50 million samples a second. And then we'll move on to adding another probe and see what the effects are there. So reference waveform, duplicate A, we'll change the colour, we'll give that a pink colour, and we'll call that was 50 ms million samples a second. Okay, so let's just get some clarification of what we've got on screen. We've got 3 waveforms now. The first one was a ×1 at a low sample rate. The next one was still a ×1 at a high sample rate. And now we'll add another ×1 test lead to FlexRay. So now we're going on to BM, B-.
Yeah, so it's in the terminology. We've done a video on terminology. It's really important that we understand what we're measuring when we say bus minus and bus positive when we're making these measurements. And it's unavoidable that terminology is the terminology.
Yes.
I suppose it's good practice to use the correct terminology.
Yeah.
But this is a bit like can high, can low.
Yeah.
That would be the thing you would sort of most logically look at. So we're now measuring, we've added, because it's a twisted pair differential bus, we've now added the second measurement, which is bus
minus. Yeah. I don't know whether the camera picked it up there, but the second I added a second probe, the dashboard chimed, and no doubt we have intruded onto the network. The network itself has recognized that there is some kind of intrusion is the only word, really.
There's a foreign object on the bus.
On the bus, yeah, something that should not be there. Let me just quickly show you, because we have checked this out before. So if I move to this tab here, you see here on the left, before we started diagnosing, no fault codes. We hadn't got a fault on this vehicle. On the right-hand side, we've now got multiple fault codes as a result of connecting to the network.
Yeah, and this is going to take you down the diagnostic garden path, or as it is there, the diagnostic yellow brick road.
Yes, yes.
This could throw you a real curveball, and because we have measured incorrectly.
Yes.
We've now introduced extra faults on a vehicle.
Yeah.
And this could be, if at best it's bad practice. At
Yes.
worst, this could really now skew your processes.
I think this is a great opportunity just to explain what has happened here. Is that we connected to FlexRay, let's go back to PicoScope, with 1x1 probe. Fine. It didn't look correct, but there was no response from the vehicle. The second I collected a second one, there was a chime. What we have is impedance inside the scope of 1 meg per channel, 1 meg ohm. When we connected one probe, we had, this is a standard impedance probe. There was no real sort of influence on the circuit. The second we added a second one, we've now got 2 mega ohm in parallel, so now we're down to 500k. Now, what's happening is the network senses this, it recognises it, and it's now influencing the packets and messaging on the network. So how do we tackle something like that? Well, first of all, we're not to use ×1 probes on high-speed networks. So let's use the guided test. That will guide us through. And you'll see certainly when we open up guided test for FlexRay, we'll choose the serial decoding option. Communication, FlexRay, serial decoding. The first one, physical layer, like we use, if you remember, with the CAN. Yeah, if we just wanted to see a single packet, that's fine, but we want streams of data so that we can pull off a lot of data in the decoder. Click on serial decoder, guide and settings file. There is the just-in-time learning.
Yep. And no point skipping this if you've never done it before, because that is if you go back, Steve.
Sorry.
That is where it tells you which leads, it's got a picture of which leads to use.
Yep, and those would be the ×10 probes. ×10, they're attenuated, but they are high impedance. So we'll just have a tidy up here, take these leads away. So once again, reference to ground, B minus, bus minus, and bus plus. So bus plus will go onto blue, bus minus onto red, channel B.
Once again, reference to ground.
Reference to ground.
Exactly like in the diagram.
Yeah. All right, so when we run PicoScope now, we'll see something completely different. Where you saw that ringing, in fact, let me just wake up the network. There we are. There is our bus traffic. I'm going to pause it at that point and let's have a look at a packet of data. Now, all of a sudden, well, what's your first thoughts on that, Andy?
Well, it looks much more like what we would be expecting.
Yeah.
And it looks very familiar to us, but it's probably worth noting at this point the voltage levels,
yes,
which were very unclear until we get to this point where we're using.
With the ringing and the overshoot, it was almost impossible to really qualify exactly where we were voltages wise. So On bus plus, we go up to 3.1 on this one and down to 2.1 with a recessive, should sound familiar, at 2.5. Then on bus minus, well actually let's go the right way. We go from 2.5 down, because we mirror bus plus, down to 2 and up to 3.1. It's 3.09, 3.1. And you see already we've got the math channel and we've got the differential and the decoder as well. So we haven't had to worry about decoding configuration. It might be worth just having a look just how many bytes. Remember, FlexRay can have 256 bytes in one payload, in one packet. What we're really interested in is using the valid. We want to make sure that all of our messages are valid. Let me have a look here. There we are, sorry, valid. So we can order by valid or invalid, and this is a complete, this is fine actually, there are no errors. And the other important bit for us really is the frame ID. That's what we're often searching for, trying to filter upon if we are trying to fathom out which ECU is responsible for a particular frame ID. We can use the decoder table for that.
So very, very thorough at the moment. Are messages being sent?
Yes.
Are they being sent and received and
yes.
understood and acknowledged? We've got all of that information on the screen for a packet of data, and we can see from that when we looked at the voltages, it's similar to CAN but different.
Yes.
And if you want to know how it's different, got the video on this protocol.
Yep.
Make sure you watch that and not just the how to test, because there's some absolute diagnostic gold involved in that. And then when you come to this bit, you can understand a little bit more what we're looking at.
Yeah, we'll have further information as well on the forum as a deeper dive. I think, Andy, you mentioned that, well, we can't go in a video right deep dive into FlexRay. No. If you wanted to know the ins and outs of each segment, each field within a packet, we've got further information on the forum. Please have a read of that, especially if this is something that you're either struggling with or certainly diagnosing. Yeah.
Or just interested and want to learn more.
Yeah, yeah. In fact, the network has gone to sleep. Let me just wake that back up. In fact, that might be quite a useful capture there. Let's just go back. There we have what is wake up. Yeah. Before we do any more, let's get that onto the waveform library.
Yeah, it's a great shout.
Yeah, because there we got bus wake up from sleep. Select, populate. Vitally important to get this right. Because it's the guided test, it's already put the channel labels in for you. Everything is fine. We're going to reduce the file size. At the moment, if we send up 3 waveforms, this would be, 40 meg. If we send just one, it's now 8 meg, so reduce the file size. We'll just I'll put a note in here for whoever is going to download this, that this is FlexRay wake from sleep. And I'll put with remote unlock, because we haven't turned ignition on.
No.
This is just the network preempting start, if you like. So the network is off and running, but it will go to sleep very, very quickly. Save and upload. Well, we will minimise that. We don't have to. I think it had just gone there, hadn't it? More haste, less speed.
Yes.
Yeah. All right, so we'll now actually turn ignition on. We'll see a lot more data coming through. So now that is full on. Actually, it doesn't really look much different, does it? I was expecting to see a lot more data come through.
I think nevertheless, I spotted an error come through there.
All right, okay, and a chime on the dashboard as well. We'll go to our serial decoder. At the moment we're on current buffer. We'll go for all buffers. Finish. So now, rather than just decoding the current buffer, you'll see now there is a new column for buffer number. And there we are. There was our invalid. So if I double click on the invalid packet, was on buffer number 6. We're currently on buffer 12. Double click that. That's taken us straight to buffer 6. And why was it invalid? Well, basically we'd come to the end of the buffer. So a message had been transmitted. Yeah, we'd started to capture it, but you see in the zoom overview, we've come to the end of the buffer, so it misses the end of the message. It flags it as an error. That is not an error. We'd be more interested in repeat errors, errors associated with the same ID.
And yeah, checking the IDs
yeah,
against errors.
Yeah, voltage as well. Voltage. Yeah, for voltage errors, this kind of thing. Probably another good one at this point to upload to the waveform library, because this is ignition on. So save, just edit the notes. This is ignition on. Just the current one will do. Save and upload. See, our previous one is there as well. All right, another technique that you will find useful is a math channel A plus B. This is what we can use for physical layer faults, for shorts to ground, shorts to positive, whatever they may be. We need to amend our math channel. So I think what we'll do is we'll open up another scope view. So we go to views, click on scope. We'll just bring this over to the right hand side, so we split the screen into columns, minimize here, and let me add the math channel A plus B. So whatever I now do in the software will be applicable to scope view 2, because scope view 2 is highlighted here in bold. If I clicked on scope view 1 and started amending controls, my controls are relevant to this view, but we want to manipulate this view over here, and we want to add a math channel, and it is A plus B. So you see there, A plus B gives us a straight line at 5 volts. Yeah. We'll just tweak the range a little bit, the scale, sorry. So we'll go for ×2, so we can bring that 5 volts right into the center of the view. There we are. And now we'll hide channels A and B. And then we'll run PicoScope. So now we really are turbocharging that, as it were. We're probably using the resources on the PC and the scope. We have got channel A raw data, channel B raw data, the differential between the two, we're decoding, and now we've also got this channel that might help us to help physical layer faults.
And the only thing we've added to the guided test now is A plus B in scope 2.
Yeah.
Because the maths channel and the decoder is all set for you, nothing to do there other than connect to the vehicle.
Yeah. We seem to be flagging lots of errors now, actually. Oh, I see, because we've still got the buffer. What I will do, I'm going to amend the decoder, because I don't want to be decoding on every buffer. I'm only interested in currently what is on screen. So finish, and you'll see here, now we've lost that buffer column. We're now just looking at packets. So we want to add something called now a mask onto scope view 2. So we go to masks, which looks to be under our more panel. There it is. If I click on the bold star, that star there, we now move the masks so it's always available here.
So it becomes a favorite.
Yeah, a favorite. That's it. So we're customizing the scope, and we also want an action as well. So now they're here without having to click on the more button. Now, what does a mask do? Well, we'll put a mask around this waveform here, this A plus B. And we'll go for generate mask from source. So you see there now that we've put in effect what would be a trap, if you like, because we are going to wait for our signal to intrude into the mask. So any change to the A plus B state, so if we were to short circuit, short to supply, we'll see it intrude into the mask, and then we can actually capture that. We want to do that hands-free though, so we need to add an action to that. So we want to be able to ask the software, when the mask fails, to stop the capture and play a sound. And we can choose a sound. Let's go for an explosion, shall we? Why not?
Why not?
Why not?
So this is great for wiggle tests, stuff like that.
Yeah, wiggle testing especially. The other one I was thinking of is road testing.
Yeah.
Obviously, you don't road test on your own, and you can't be operating the laptop and driving at the same time. But you could have this configured before you set out on road test, so that you can do what you've got to do, generate the fault. When it's safe to do so, pull over, review the data. But wiggle testing, yes, yeah, absolute perfect. So what we'll do is we'll introduce a fault onto the system and see if the software catches it for us. Just noting here in the bottom corner, we see that we've got the mask A plus B. At the moment, 51 passes. In other words, 51, 56, now it's counting up. There have been no errors. Okay, so we're now configured. We've run the scope again. We've put more time on the screen so we can actually see the event. Hopefully a period of transmission, then a short to ground, whatever it may be. We chose to short, or we will short, BM bus minus FlexRay low to ground. At the moment, 18 passes. Let's see what happens now when we short that down to ground. There we are. So the software has captured, we can see clearly the event. We can go back through the buffer. So it was just at the end there. And we can click on the waveform navigator and ask it to show us all captures, or just show the mask failures. Okay, so it is number 14. It was the end buffer because we'd asked the software to stop when the fault was detected. Let's run the scope again. Let's put more time on screen. Let's increase sampling because we want to be 5 times. So let's go to high. Let's try that again. So sampling, not buffer memory, sample rate. Fast, there we are. So we are 50 million samples. Because we've changed the time frame, we need to now edit the mask. So we go back to the mask editor, create mask from source, that's better. We can trim the mask as well. We can actually modify it so we can get our tolerances even tighter. So you see there, the mask is getting closer to the signal. We'll try our look at that one. Okay, so we now have 2 passes. Because we've got the decoder on, we're really asking a lot from PicoScope. It can deal with this. Nevertheless, you can see that it's taking time to update because we're pulling in all this data, then we're decoding. We'll delete the decoder. So pause the software, delete the decoder. There we are. Run PicoScope. That's better. Okay, we'll introduce a short B minus down to ground. Ah, there we are. That's perfect, isn't it? And we've asked the waveform navigator to show us the mask fail so we can see, well, I think that speaks volumes, doesn't it, Andy, that we are, an event has taken place there. We can see, in fact, that is, let's make maximum use of PicoScope zoom feature here. When we zoom in on the signal, let's draw around this area here. We can clearly see which signal went down to ground. If I click on the views option and auto arrange, if I pull this ruler down here and type in 0, yeah, BM, bus minus. And interestingly enough, even though bus minus was down to ground, we still had what looks to be an attempt to transmit here.
Yeah.
Yeah.
And that shows, you know, the fault tolerance and the robustness of these twisted pair networks.
We saw this with shorting, was it CAN low, down to ground in the previous video. The CAN high still tried to maintain communication and did so successfully as well. Yep. So what we'll do, we'll send that to the cloud, so send it to the waveform library. We'll give it a name, FlexRay short on BM. The current one, everything is correct here. We've got our text here to support what's going on. We'll save and upload. That will join the other files in the library from our FlexRay video, FlexRay captures. All right, we'll have a little bit of a tidy up here because what I want to now do is just show you another tip that you may find useful. We're going to introduce a new probe now. This is our differential probe, and as the name implies, rather than measure reference to ground, we're going to measure across FlexRay high, FlexRay low. So here we have our differential probe. This is high impedance. So using a single channel now, thank you, we can connect directly across bus plus and bus minus. We'll take away math channels because they're not required anymore. We're just going to do a FlexRay capture. Let me take A minus B. Sorry, that's still loaded from the guided test. There we are. We'll take away the trigger, none, and we'll maximize the range. And when we zoom in, we've actually got, let me pause the scope and just choose a packet here. In effect, our differential math channel. Yeah, but just using one channel, so there's no maths required here. This is simply using our differential probe connected across the network, across bus plus, bus minus. What I like about this technique is you've now got 3 extra channels. It hasn't cost you 2 channels.
2 channels, yeah. And you can use this technique with any of the twisted pair networks in a similar fashion. What you need to understand is the difference in the measurement technique. What we're measuring now is, I'm displaying, is the voltage difference on the bus.
Yes.
And if you understand how the network works and you use this measurement, as you say, you're very economic with your channel use.
Yeah. Which is all important when we're diagnosing, because with 3 more channels now, it could be that we may want to analyse ignition or even just using an accelerometer for undulation in the road. It may be that when you hit something in the road, the FlexRay goes offline or there's an event in FlexRay. Having the accelerometer on there means you would capture that event. There's our voltages now, so +1, -1, as we described, because now we're measuring across. Our recessive voltage is 0, and we can apply the decoder to that. So if we go to serial decoding, we will go FlexRay. It's channel A. There's a tip here, we need to invert when we use the decoder. Only for FlexRay, when the signal is in this orientation. We'll use the center as 0 as our crossing point, and we'll go for 500 millivolt, which is halfway. And yes, that should cover us. The baud rate, 10 megabit per second. We can confirm that, but we will measure that. Just the current buffer. There's no rulers to decode between. It's waiting for data. There we are. So we're proving there that we are not influencing the network, we have not introduced faults, and we can decode successfully. And on that note, shall we just confirm that that this is a 10 megabit per second network by, just scale up a little bit, we choose a small bit, and we should be looking for, where are we? Let's go with, yeah. If I was a little bit more accurate, you could see there that we are 9.751 megahertz. Yeah, measuring the smallest bit accurately, that should be 100 nanoseconds. 100 nanoseconds translates into 10 megahertz, 10 megabit per second.
Okay. And all doing it using one channel.
One channel, yeah. It's a a valid accessory that gets you out of trouble. You could not do this with a ×1 probe. You couldn't do it with a ×10 probe actually, because we only have the high impedance on one side. So yeah, using the diff probe gets you out of jail 100%.
I think once again, Steve, we've proved that using the CAN process for network diagnosis, we're really concentrating our messages being sent. We've demonstrated a number of different techniques, the good, the bad, and the damn right ugly of measuring high-speed networks.
Yes.
But I think the differential probe at the end shows that you can use one channel, get all the same information. Because whatever happens on either one of the twisted pairs will affect that. Obviously, once you see something that's wrong, CAN or R messages being sent, that will give you everything you need to know with a single connection. Nothing wrong with doing it, measuring both channels.
Yes.
But you've got to make sure you're using the correct probes, because you don't want to introduce faults on the vehicle by your measuring technique.
Yeah. Nothing either wrong with using the differential probe to measure reference to ground. You could, if you wanted to, use B plus to reference to ground, B minus, you could use that, but why not measure across? Yeah, a winner. Okay, so that takes us, or completes FlexRay, so thank you for watching.
Thank you.